What's up, everybody? In this video, we're going to cover USACO's 2021 December contest at the silver level, problem number 2, connecting two barns. Farmer John's farm consists of a set of n fields, where n is between 1 and 10 to the 5th, conveniently numbered 1 through n. Between these fields are m bidirected paths, where m is from 0 to 10 to the 5th also. Okay, so what this is saying is the number of barns, 2, 3, 4, up through n at most can be 10 to the 5th. And there's paths connecting them. For example, 1 could be connected to 2, that's bidirected. 2 could be connected to 3, 3 could be connected to 4. With a maximum of 10 to the 5th, actually I think it should be 10 to the 5th minus 1, we could potentially connect every single field to every other field, or we may have paths missing, or we may have as few as no paths at all, and every field could be completely separated. The farm contains 2 barns, one in field 1, and the other in field n. Okay, so our very first field has a barn, and then our very last field has a barn, whatever. And the rest of the fields are just fields. Farmer John would like to ensure that there's a way to walk between the 2 barns along some series of paths. He's willing to build up to 2 new paths to accomplish this goal. Due to the way the fields are situated, the cost of building a new path between fields I and j is I minus j quantity squared. Okay, so for example, if I is 1 and j is 2, the cost would be 2 minus 1, which is 1 squared, which is just 1. But if we wanted to build a path from 1 to 3, then we'd have 2 squared, which would be 4. Here, this would be 9, and then 16, and so forth. So we really want to build short bridges. It is to our advantage to build multiple short bridges rather than a singular long bridge. However, we are only able to build, I guess they're not bridges, they're paths. But we only can build 2 paths. We can't build more than that. So we're looking at trying to figure out how to connect this barn to this barn by adding at most 1 path and then perhaps another path. Due to the way fields are situated, please help Farmer John determine the minimum cost needed such that barns 1 and n become reachable from each other. So we don't have to connect everything to everything, but we do need to make sure the first one is connected to number n, whatever that is. It's a pretty short description. It's actually kind of a long problem though. Input format. Input arrives from terminal and standard in, so it's just typed in. Each input test case contains t subcases, where t is between 1 and 20, all of which must be solved correctly to solve the input case. The first line of input contains t, after which t subtest cases follow. Each subtest case starts with 2 integers n and m. Next, m lines follow, each one containing 2 integers I and j, indicating a path between the 2 fields I and j. Let's slow down and go through this a little. So this is they're explaining this in a lot of detail because I think this was the first test that actually used this multiple subtest case thing. I'm going to make a video that specifically goes into dealing with these subtest cases, but essentially what this is compared to any previous problem is this first number is how many test cases there are, and then this would be like in past problems. This is what you would have to deal with. That's a test case. But then now this is a second test case. They have them both rolled up into one. My recommendation when you're writing code is to write your own test case where there's only 1 test case, your own sample data where there's only 1 test case, and then just take the first test case, 5, 2, 1, 2, 4, 5. This makes it a little easier for testing. It kind of lets you focus on a single test case, and then it kind of reduces the amount of output as you're trying to trace through something that might have gone wrong. You don't have to worry about having output from both of them. But yeah, essentially what this is then is saying that the first line is t, which is how many subtest cases there are. If we then look at this 5, 2, 1, 2, 4, 5, we can treat this like what would have been a test case. So each subtest starts with 2 integers n and m, n and m. In this case, that's 5 and 2. We have an n and an m here for the first test case, and then an n and an m here for the second test case. The next m lines follow. Each containing 2 integers I and j, indicating a path between 2 different fields I and j. So for example, field 1 connects to field 2, field 4 connects to field 5. That's the first of these 2 subtest cases. It is guaranteed that there is at most 1 path between any 2 fields. It is guaranteed that there is at most 1 path between any 2 fields, and that the sum of n plus m over all subtest cases is most 10 to the 5th. I guess here they're saying that there wouldn't be 2 connections, like 1 to 2 isn't going to appear another time later on. And the sum of n plus m over all subtest cases is at most 5 times 10 to the 5th. Basically, they're giving you some hints as far as the complexity. The sum of n plus m, which is these 2 numbers, is at most 5 times 10 to the 5th. Generally speaking, when you're looking at this 10 to the 5th, that again is just means like what it did before, which is you're going to try and not do an n squared algorithm. This actually is fairly straightforward to write as an n squared algorithm, but we're going to have to optimize on that. We'll get into that, how that's going to work in a minute. Output format, output t lines. The ith line should be should contain a single integer giving the minimum cost for the ith subtest case, right? So we can see the 5, 2, 1, 2, 4, 5. That's the first test case. The answer for that one is 2. Second test case is this one, 5, 3, and then there's 3 paths, 1, 2, 2, 3, and 4, 5, that at a cost of 1. The cost is what you're ultimately having to put out. So let's see, and then it says here, in the first sub, let's actually write these subtest cases out. So I've got 1 to 2 in the first case, 3 by itself, and then 4 to 5. So that's a path from 1 to 2 and a path from 4 to 5. You've got your barn at 1 and a barn at 5 that you have to connect. So in order to connect that, you have 2 options. You either could connect 2 to 4 directly for a cost of 2 squared, which would be 4, or you could connect 2 to 3 and 3 to 4, which would be 1 plus 1. Technically, I guess you could connect straight from 1 to 5 for a cost of 16, but again, that would be inefficient. You're looking at the lowest cost, but there are a lot of possible combinations. And actually, this is what the algorithm really has to be smart about, is making sure that you're not doing stuff like this, connecting 1 to 5, connecting 1 to 4. I mentioned earlier that an n squared algorithm is quite easy. The way an n squared algorithm would work is you would check the connection cost from everything to everything. So 1 to 3 would have a cost of 4. 1 to 4 would have a cost of 9. 1 to 5 would have a cost of 25. 2 to 3 would have a cost of 1. 2 to 4 would have a cost of 4. 2 to 5 would have a cost of 9. 3 to 4, it's a cost of 1. 3 to 5 would have a cost of 4. 4 is already connected to 5. Then what you would do is you would try and trace through and say, okay, so what is the node that has the cheapest way to connect to a member of each group? And you'd have 1 plus 1, which would be 2. We're going to find a better way to do this than n squared, though, because this isn't going to work on a large test case. But yeah, what they're saying here then is, let me clear all these paths out. Okay, so what they're saying is in the first subtest case, it is optimal to connect field 2 and 3 with a path, and then 3 and 4 with a path, right? Of course, because 2 to 3 can be connected at a cost of 1, 3 to 4 with a cost of 1. In the second subtest case, optimal to connect 3 and 4 with a path. The second subtest case is pretty much the same, other than they already have 2 and 3 connected. The reason they're pointing it out is to show that it is possible to connect the first group directly to the next group. We don't necessarily have to have an intermediary node. And actually, since they mentioned the maximum paths are 10 to the 5th, there's probably a test case where everything's connected to everything, and you should have an output of 0 in that case. So let's talk about the optimizations that we're going to need in order to get this figured out and running in the correct time complexity. So let's say like I have red represents a group of nodes that are all connected to each other. We've got here, here, here. We're going to have 1, 2, 3. And let's say like I have, this is connected to here and here. This is connected to here, here, here. And let's say like I have, I'm going to use blue in the middle. It's like I have 2 blue nodes in the middle. And we'll just imagine that then there's some other nodes that are blocking us here, green, green, and we'll put a blue node at the end. So I've got a barn at this blue node. I've got a barn at this red node. And I want to try and get these connected. The blue nodes are all connected to each other. So I've got here, here a connection. And then the green nodes are connected to each other as well. So as far as optimizations, if I'm trying to figure out what is the cheapest way to connect red to blue, then ultimately what I want to do is I have a red pointer here. I have a blue pointer here. Now, there's no reason to connect this node to the blue node. There's no reason to connect this node to the blue node. We may want to try and connect the one that's right next to it, though. So what you're wanting to do is you're wanting to try and figure out a way that you don't have to compare every node to every other node. Ideally, the only 2 nodes we really need to check to connect to this node are the 2 red nodes that are closest to it. We don't want to check that one. We don't want to check that one. We don't want to check that one. We don't want to check that one, because any of those are going to cost more because they're further away than the 2 red nodes that are closest to that blue node. So the way that specific mechanic is going to look is when I'm iterating, if I'm trying to find a way to connect to this blue node, when I advance the red pointer to the next one, if the red pointer is already at a location that's greater than the blue pointer, I'm going to stop my iteration. And then I'm going to take only 1 step back to go to this previous node prior to advancing the blue pointer. So then I would advance the blue pointer to this node. Then once again, check that distance. In this case, this would be 2 squared, which is 4. advance my red pointer only one step, but not any further away. Check that connection would be 1. And then again, taking one step back with the red. Ultimately, what you're trying to do is you're trying to figure out how to get the two barns connected. And the way you're doing that is, assuming they're not connected at the start, then what we're looking for is we're either looking for a way to directly connect red to blue, which would close it, or if we had a different color in the middle, let's say, for example, like these two middle nodes were green. Swap that, green, oops, green and green. So those are connected, these are connected. In this case, it's a little trickier, but my goal ultimately is going to be, how do I get the red group, any member of the red group, connected to any member of the green group, and then any member of the green group connected to any member of the blue group, if the blue is a group. So if you think, I'm going to write that out. So if I've got red here, and then I've got blue here, L-U-E, and I'm trying to figure out how to connect those two. Either I'm going to connect red to blue. That's one possibility. I may directly connect red to blue, or I need to figure out what color, for example, green, green, and then maybe let's go ahead and put a yellow one in there just for giggles. Let's throw one yellow node in there. One yellow node, oops, and then we'll connect those red ones. That, would it be green or would it be yellow? In that case, my options really are, I need to figure out, is there a way I can connect from red directly to blue, or from red to green and then green to blue, or from red to yellow and yellow to blue? And this is for however many groups there are. There may be 10 to the 5th groups technically if there are no paths. But that's the high level solution I'm looking for, is either can I connect a red node to a blue node, or is there an intermediate node, either an intermediate group, either the green group or the yellow group, where I can connect red to that group and then that group to blue. Let's look at the numbers here. So my best connection, just pretend we'll be omniscient for a minute and just kind of eyeball it. If I were to directly connect red to blue, this is probably going to be the best bet. You want the closest two nodes, and these are the closest. That's actually, there's only one blue node, so it's simple. So that cost there is going to be, was that 1, 2, 3, 3 steps squared, which is going to be 9. My cost from red to yellow, cheapest cost from red to yellow would just be any one of these two. These both are cheap. So my cheapest cost from, let me switch back to yellow. Let's get that here. My cheapest cost from red to yellow is going to be 1. Let's switch back to black. Red to yellow is going to be 1. But then my cheapest cost from yellow to blue is going to be, let's see, 1, 2, 3, is going to be 16. So 1 plus 16 is going to be 17. That's not very good. We already have a better solution directly connecting red to blue. Final, how much is it to connect red to green? I could connect red to green either here or here. There's a couple options for that, or here. That's going to be a cost of 1. And then from green to blue can be connected here for a cost of 1. So that's going to be our winner then. My cheapest path is going to be connecting red to green and then green to blue. I'm going to switch over here so I have a little more room to draw. Red to green and then green to blue. So the question then is, how do we do that with an algorithm, and how do we do that in a way that's organized? Starting from, again, kind of very high level, and then we'll kind of gradually get deeper and deeper into this. So starting from here, essentially what you're going to be looking to do is you're trying to figure out what is the cost to connect from any red node to some particular node, and then the cost to connect from that node to any blue node. For example, if I were to go and fill this in, my cost to connect this one to red is 1. Oops, 1. My cost to connect this one to red would be 1. My cost to connect this one to be red would be 1. My cost to connect this one to red would be 4. My cost to connect this one to blue is going to be, geez, what is that? 1, 2, 3, 4, 5, 6, 7, 49. My cost to connect this one to blue would be 36. This one would be 1, and this one would be 4. So then what you're doing, and then your cost to actually connect this one, the yellow one, to red would be 1. Your cost to connect this one to blue would be, what did I say that was? 1, 2, 3, 4, 16. So then what you're looking for is, of everything in the green group, what's the cheapest connection to red, which in this case would be 1. And then what's the cheapest connection to blue, which would be this one. So the green group as an intermediate would be 1 plus 1. The yellow group, on the other hand, we've only got one option, and it's going to be 1 plus 16, which is 17. And then the cost to connect directly from red to blue, if we were to have the cost from red to red here, this would be 0. The cost from here to blue would be 9. So your connection using this node, directly connecting red to blue, in this case, like red's like your intermediate group. If you use red as the intermediate group and also the starting group, then your cost to connect to red is 0. Your cost to connect to blue is 9. So for the red group, we've got a cost of 9. For the yellow group, we've got a cost of 17. And for the green group, we've got a cost of 2, which is the best. So what we're looking to do is ultimately how to fill out these numbers. How much does it cost to connect to the red? How much does it cost to connect to the blue? And we're also going to want to do that by group. And we're going to want to sort by group. Our initial setup, though, doesn't really tell us the groups. Our initial setup gives us just the connections. So 1 to 2 is a connection. And then 4 to 5 is a connection. But then when we have our nodes, 1, 2, 3, 4, 5, it's up to us to figure out what the groups are and how to build that. So let's start with walking through how we're going to get these things into groups. You may have done a problem before that's called, I think, milk visits, where Farmer John has to walk a visitor from one location to another, and you have to check to see how many, whether or not you pass through every type of milk. If you've done that problem, this might be familiar to you. If not, this might be the first time you've seen this. But essentially what we're doing is we're trying to figure out what group each of these barns is in, or each of these fields is in. So in the beginning, we start off with an array. This is the most common way this could be done. And every group, every barn is, or every field in this case, every field is put into group 0. And what we want to do is a depth first search. Easiest way to do this is going to be with some sort of a recursive search. So for example, if I were to do depth first search, and I were to call that with 1 as my current field, and then 1 as my current group. So like I want to start with group 1. So group 1, I see that I have a 0 here. I can't have anything in group 0, so I'm going to call depth first search with 1, 1. What that's going to do is go to field 1 and assign it to group 1. So then this becomes a 1. And then it's going to check through your connections. Hopefully you've got this in some sort of an adjacency list that you can do quickly. And we'll talk about adjacency lists in a minute. But essentially what's going to happen then is you're going to look for anything that barn 1 connects to, or field 1 connects to. In this case, field 1 connects to field 2. So then we would recursively call DFS with 2 as our node, and then 1 as our group. And that would go through and assign node 2 to group 1. We then would look through and see if there's any other paths connecting to. In this case, we've got a connection from 2 to 1, but 1's already got a group, so we don't need to recurse. We have no other connections, and then that ends it. And then group 1 is finished. Group 1 then is going to contain nodes 1 and 2 only. We then move on to group 2. Since then we were at 1, we advance forward. We find this is the first one that doesn't have a group. So now we call our DFS with 3 as our node and 2 as our group. So that would then assign group 2 to field number 3. We would look through our connections. Nothing connects to field 3, so there's no recursive call, and then that's done. And then advancing forward from here, we find field 4 is in group 0. Oh, sorry, this should be node 3 is in group 2. For group 3, we have node 4 has no group, so we're going to call DFS of node 4, field 4 with group 3 as our target. We look through our connections up here. Wait, that actually needs to assign this to group 3 first. 3. We look through our connections up here. We see that we have a connection from 4 to 5. So then we're going to call DFS on node 5 with 3 as our group. And that's going to assign this one to group 3. Then afterwards, we'll analyze that and say that we have 4 and 5 in group 3. So this is how you then build your groups. You've got group 1 containing 1 and 2, fields 1 and 2, group 3 containing fields 4 and 5. From here, I just kind of color coded it. But then what I did is I said, okay, so group 1 includes 1 and 2. So 1 and 2 are in the red group. Group 2 contains only 3. So that's group 2. And then group 3 would be like my blue group, group 3, group 3. So that's how you get your initial farms. When you have that, let me clear off this DFS stuff. When you have that, then this is where you start actually iterating through and trying to figure out how these guys connect to each other. So in this case, then you would say, okay, well, I want to have I running through and figuring out, like basically a for loop, running through each of these nodes and figuring out what's the cost to connect to red, what's the cost to connect to blue for each of them, the nearest red, the nearest blue. We'll talk about how that algorithm is going to work in more detail in a minute, but just kind of eyeballing that. Cost to connect to anything red to red is always going to be 0. Cost to connect anything blue to blue is going to be 0. The cost to connect each of these to blue is going to be the cost to connect to the closest blue one. So in this case, this is 3 squared, which is 9. And then this is 4. When your I is advancing to here, it's going to check cost to red is going to be 1, cost to blue is going to be 1. When I is over here, cost to red is going to be 4. And when I is here, cost to red is going to be 9. Once you have that information put together, for each group, you want to try and get what is the cheapest connection to red and the cheapest connection to blue. So for group 1, your cheapest connection to red is 0 because it's already in group 1. And your cheapest connection to blue for red is between 9 and 4 here. It's going to be 4. So 0 plus 4 is your cost to connect red to red, obviously, which is free, and then from red to blue. Next up would be group 2. We use green for that. Our cost out of all our nodes here, cheapest cost to connect to group red group is going to be 1. Cheapest cost to connect to the blue group is going to be 1. So I've got 1 plus 1, which is equal to 2. And then finally for 3, cheapest cost to get to red is going to be 4. Cheapest cost to get to blue obviously is 0 because it is blue. So I've got 4 for that, 4 for red, and then 2 was our cheapest cost here, which was green. Okay, I mentioned adjacency lists. Let's talk about that. There's a lot of tools you need in order to be able to do this. What an adjacency list is for every single node, for example, node 1, you have to know what nodes you connect to. So when I'm initially loading this up, so like when I'm doing my file reader. So I've got, actually, let's use this one. It's a little bit of a bigger test case. So I'm going to do a file reader using the second test case here. What we're going to do then is we're going to say, okay, so as I'm reading this file, I'm going to look at every connection and I'm going to push back its neighbor into some sort of list of lists or vector of vectors or, you know, whatever it is your data type is. So what I'm going to do then is I'm going to say, okay, I've got 5 total barns. So I want to know, what does barn 1 connect to? What does barn 2 connect to? What does 3 connect to? What does 4 connect to? What does 5 connect to? Essentially what I'm, excuse me. Essentially what I'm doing there is I'm making a list of lists. So my outside list is going to be containing 5 inside lists, 2, 3, 4, 5. And again, if you're using Java, you can use array lists. For C++, you can use vectors. Python, you know, it's just lists of lists. And then as you're reading the file, for example, I've got a connection between 1 and 2, then to list in index 1, I add a 2, and in index 2, I add a 1. I see 2 and 3. So in index 2, I add a 3. In index 3, I add a 2. Then I've got 4 and 5. So index 4, I add a 5. Index 5, I add a 4. Once I do this, I now can see what all of my nodes connect to. I've got 1 connects only to 2, that's a list. 2 connects to 1 and 3, that's a list. 3 connects to 2, that's a list. 4 connects to 5, that's a list. And 5 connects to 4, that's a list. Most of these lists only have 1 item. When I then get into figuring out how to assign my groups, we were talking about that, that DFS a minute ago. For group assignment now, when I write my function, my DFS function, I'm going to take in first the node that I'm currently at. For example, let's do node 1. And the group I'm trying to assign it to. Let's also go ahead and do group. Let's do group A so that it's not a number, kind of make it a little distinct because otherwise the ones and ones feel a little confusing. So if I want to do DFS with 1 and assign it to group A, then essentially I'm going to have to look and see what does 1 connect to. And 1 connects to 2, which means I'm then going to call DFS 2 with group A. When I get to 2, and then I'm going to loop through all these connections, and I'm going to be doing DFS 1 to A again, which, you know, again, we can either filter that out by making an if statement check to make sure that the thing we're connecting to doesn't have a group yet, or we can make it so that we have a base case in our recursive function call that checks to see if a group's assigned, and if so, it returns without doing any recursion or any assignment. And then we're also going to be calling DFS on 3, DFS on 3 from 2. So 2 is going to call this one and also this one. So what's happening in your DFS is you're looping through whatever node you're currently at. You can look it up on this adjacency list. You loop through what its connections are, and you make your recursive call on each of those connections. So if I were to write that in a little bit more of a comprehensive thing, if I have DFS of my current node, I'm going to write N for node and then G for my group. Then what I'm going to do is I'm going to check to see if we already have a group. If group of N not equal to 0, essentially, which means we're going to have some sort of a group list. And again, we could make this a global variable, or you could have that be an additional variable that gets passed in. With With C++, you have to watch out. If you pass a vector, it'll make a copy of the vector. With Java and Python, you won't have to worry about that because they always pass by pointer. The other option is if you were to declare, if you're using C++ and you declare it as like a double pointer or something like that, then you can pass that. And then if you modify it inside the function, it'll stay modified. The other option is I think you can do vectors as pass by reference. But honestly, if you're doing C++, I would just make a global variable. That'd be the easiest way to do it. Have some group variable that has a size of 10 to the 5th. Declare it at the very top, way before even your main even starts. Get that set up, and then you can just write to it. That'll reserve the memory. I think that even actually is optimized to reserve the memory prior to running the program, which probably saves a little bit of time than reserving it dynamically. But however you decide to do that, if you want to do that, or if you want to pass it in as an argument, if you're in Java, you can make a static variable actually as well. But anyway, you set that up, and then if your group for that particular node is not equal to 0, then it's already got a group. And if it's already got a group, then you can just return. And then you can call that your first base case. Otherwise, what you want to do is your nodes that you can connect to are going to be whatever is in your adjacency list that we made earlier at the value of n. So, if I have 1 with 2, 2 with 1, if this is my adjacency list, 3 had nothing, 4 had 3, 4 had 5, sorry, 5 had 4. I think 2 had 1 and 3, and then 3 had 1 in that example. Or no, 3 had 2. If this is my adjacency list, then what I'm doing is I'm looking at node n, which, for example, if I'm currently on node 2, is going to be these nodes right here. I'm getting those nodes and I'm putting them into my nodes variable. Then what I'm doing is for every node in nodes, I'm just going to recursively call my DFS, passing in that new node that I can get to, that neighbor, the same G, the same group that I'm trying to assign. And then, again, if this is being passed in our global variable or whatever. And then that's going to go through and assign groups to all these things. What you're going to end up with then is you're going to have your groups, group 1, for node 1, 2, 3, 4, and 5, what groups it's in. Nodes 1, 2, and 3 in this example are all going to be in group 1. And then 4 and 5 would be in group 2. And then these are how you're going to be making your groups for as far as figuring out what your solution is. You want to know then what is the cheap of all the things in group 1, what's the cheapest connection to red, what's the cheapest connection to blue. Of all the things in group 2, what's the cheapest connection to red and blue. And then same with group 3, same with group 4, and so on. And then that's going to plug back into your original solution. Okay, one more thing we're going to have to know how to do in order to do this. I was kind of talking about this a little bit earlier, but I want to go into this in more detail. When you have those, how did we have it? When I did like 1, I think it was 1, 2, 3, and then 1, 2, 3, and then some nodes in the middle that may or may not connect to something further down the line. We'll just say that we're not really sure like what that's connected to, but those might connect to something further down the line. It also is possible what they connect to may be way, way past where this red ends. So we do need to know, we do need to know what the cheapest connection is from red to black, even though there are red nodes that are ahead of this, because again, there may be a black node way, way, way down in that direction, and that might save us a whole lot of cost. But essentially what you're looking to do is you're going to have some sort of an eye counter that's going through all your nodes, and then you're going to have this red pointer. And your red pointer then is going to be looking at the nodes that are in group 1. When we did the DFS, we're going to know what nodes are in each group. Whatever nodes are in the first group, we want to be able to check the nodes that are around where I is. So I'm going to advance to here, but then when I'm past I, I'm going to roll back, and then I'm going to advance I to the next location. Then once again, I'm going to check from here. I'm going to advance. When I realize I'm past I, I'm going to stop, and I'm going to go back to the previous location. And then I is going to proceed forward yet again. But we're never going to let that red pointer get too far ahead of I. Once it's one step ahead of I, it doesn't need to go any further. So let's look at a little bit of a larger scale map here. I have one more map that I want to go through. Let's see here. I have 3 reds. 1, 2, 3. 1, 2, 3. We'll do the full algorithm kind of top to bottom. I have 2 greens. 1, 2. I have 2 reds again. 1, 2. I have 2 more greens. 1, 2. I had 2 yellows. 1, 2. I have a blue, 2 yellows, and a blue. Blue, 2 yellows, and blue. I made this one up earlier because it covered a couple cases, a couple edge cases that I think are important. Okay, so we've got all these nodes. There should be 15 of them. I'm going to go ahead and number them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So when you read the file, what you would see initially is all of your connections. So I'd have a connection from, and I won't write them all out, but 1 to 2, 2 to 3, 3 to 6, 6 to 7. Maybe we'll write them all out. 4 to 5, 5 to 8, 8 to 9, 10 to 11, 11 to 13, 13 to 14, and then 12 to 15. Let's switch back over to the blank page here. So my initial file read, this would be the test case, and I have, what is that, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11. If you want to run this test case, that actually might be kind of interesting. And I have 15 nodes. Okay, so I have 15 nodes, and this is one test case if you want the whole thing. I have 15 nodes. There are 11 paths. My connections are 1 to 2, 2 to 3, 3 to 6, 6 to 7, 4 to 5, 5 to 8, 8 to 9, 10 to 11, 11 to 13, 13 to 14, and 12 to 15, if you can read all these chicken scratch marks. Okay, so my depth first search, first thing is going to do, well, the first thing I'm going to do is I'm going to load this up into an adjacency list. So what does node 1 connect to? What does 2 connect to? What is 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, so node 1 connects to node 2. Node 2 is going to connect to node 1 and node 3. Node 3 connects only to 6. Node 6 connects only to 7. 4 connects to 5. 5 connects to 4. 7 is going to connect to only 6. 8 to 9 and 5. I have 5 to 8, 5 to 8, 4 and 8. Yep. 9 would connect to 8 only. 10 to 11. 11 connects to 10 and 13. 12 connects to only 15. 13 connects to 11 and 14. Can't read this. 14 connects only to 13, and 15 connects only to 12. So first thing then is to do our DFS. What our DFS is going to try and do is assign group numbers to each of these. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. We'll kind of just briefly run through how this works. So I'm going to call my DFS with group 1 on node 1. It's going to put node 1 in group 1. It's going to iterate over the children and see group 2. It's going to node 2. It's going to assign 2 to group 1. Iterate over the children. It'll see 3. It'll assign 3 to 1. Iterate over the children again. For 3, it's going to find 6. 6 gets assigned to 1. Iterates over 6's children to find 7, and that gets assigned to 1 as well. 7 will only find 6. We don't need to recurse on anything else, and that's going to put all those into group 1. Next DFS that's going to be called is going to be from node 4 to assign to group 2. So node 4 gets assigned to group 2. That's going to pass on to 5. That's going to pass on to 8 and 9. My next DFS is going to be from 10 for group 3. And then 10 is going to be put into group 3. 11 is put into group 3. 13 is in group 3. And 14 is in group 3. Finally, DFS would call on 12 for group 4. And that's going to put 12 and 15 into group 4. Group 4. Okay. Next thing we have to do is we're going to have to put these into some sort of a structure. I'm going to go ahead and erase this test data here. That's going to put us into some sort of a structure where we know what nodes are in each group. What nodes are in group 1, what nodes are in group 2, what nodes are in group 3, what nodes are in group 4. Group 1 contains nodes 1, 2, 3, 6, and 7. Group 2 is going to contain 4, 5, 8, and 9. Group 3 contains 10, 11, 13, and 14. Group 4 contains 12 and 15. Where's my DFSs down here? Okay. So then what we're going to do is we're going to have a red counter start at 0. Clear this all out. We have our red counter start at 0. We have our blue counter start at 0. That's the index of which red node we're looking at. So for example, since since red is in group 1, your red counter at 0 indicates this node 1 right here. Since blue is group 4, it's the highest number group, obviously, then our blue counter being at 0 represents this node right here, the 12 node. And I'm going to go ahead and draw those with a red arrow and a blue arrow. So we've got a counter that's looking at this node, and we've got a blue counter looking at this node. And now what's going to happen is we have a for loop, and I is going to start at this first node, I here, I equals 0. And it's going to work its way through all these. And for every one of these, we're going to try and figure out what's the cost to connect the node to red, what's the cost to connect the node to blue. And we're going to calculate that using this red counter and this blue counter. So we're going to start with I equals 0. We're going to say, okay, so I equals 0. Red counter currently is looking at node 1. I equals 0. If I were to, let's actually just make I equal 1 to make life easy. If I is at 1 here, which is the first node, I'm 1 indexing because that's how the problem did it. If I is at 1, then I look at my red counter. My red counter is indicating node 1. My I is indicating node 1. The total cost of that is 0. So in my red area here, I'm going to put a 0. Now, the way you could represent that is for each group, group 1, group 2, and there's a lot of ways you could code this, group 3, group 4. You could have what is the cheapest cost to connect your group to red, and the cheapest cost to connect your group to blue. So if I wanted to have like red and blue, then I'll have infinity, 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 or if you want to use int max or whatever. Red obviously connects to blue. Red obviously connects to red for free. So that's group 1. Blue is going to connect, group 4, which is blue, connects to blue for free. So that's going to be also free. So then as you're going through, you're going to be checking your cost here and seeing if it's cheaper. And the very first one is going to realize that your cost to connect to red is going to be 0, and it's going to dump that in over top of the infinity. We actually don't even really need to fill that in explicitly ahead of time because it's going to solve that as it goes. So figure out your cost from node 1 to the first node of node red. If your red counter is to the left of I, we can advance it. But since right now the red counter is indicating node 1, there's no reason to run the red counter this way. There's not going to be a later node that's going to connect back to this one that's going to be cheaper. And we're already on red anyway, so but that'll make more sense when we get to green. So we don't need to advance the red counter. We do need to check blue though. So checking blue, the cost from here to blue is 1 to 12 is 11, that's 121. That is cheaper than what we've seen so far because we had an infinity. So we'll go ahead and write a 121. Group 1 can be connected to blue for a cost of 121. That's the cheapest we found so far. That's 121 right here. Now that we've done red and blue, we can advance the I. So I is going to then advance to 2. So now our cost to get to the node where the red counter is 2 to 1, which is a cost of 1. Let's mark that down here. But because the red counter is to the left of I, the red counter is allowed to advance. And the red counter only advances when I is to the left of it. So, oops, let's do that in red, make that more clear. Red counter is going to go here. Cost then to connect from here, since now I is equal to 1, or the red counter is equal to 1. That's now indicating the second number. Go ahead and underline that in red. That's indicating the second number in group 1, which is 2. If I is 2 and group 1's red counter, which now is going to be 1. Let me mark that down here. Red counter is now at 1, indicating item 1. Then the cost from 2 to 2 is going to be 0. That's cheaper than this, so that'll become a 0. 0. And then connecting to blue, I've got 2 to 12, which is 10, which is a cost of 100. And again, because this is indicating, the blue counter is indicating 12, because blue counter is on 0 right now, and that's the first item in group 4. And then you have 100 now is for red is a cheaper now. It's a cheaper way to connect to blue, because the red group now, which is the group that red counter or that I is currently indicating. Sorry, I here on node 2 is currently indicating the red group, so we can mark that the red group's cheapest connection to blue, or rather group 1's cheapest connection to blue is now 100. And again, I mentioned earlier, there's no reason at this moment to advance the blue pointer away, because we don't ever want to move blue away from I. Both the red counter and the blue counter always want to stay as close to I as possible, so we don't move away from them. We only can go a step past them. Likewise, there's no reason that in this case that we should go past it, because we're already on it. So there's no reason for the red pointer to advance either. Red pointer, blue pointer don't advance, and then I can progress to the next number. We'll speed this up to get to the green, because that's going to be more interesting. So the I, whoops, let me erase that. I is here. This was 100. Okay, so I is here. Once again, red's going to see 0. This is going to be 81. The red counter is going to advance. The blue counter is not going to advance. And then we're on to the next I. Let's get I over to these green ones, because that's when the algorithm starts getting kind of interesting. Oh, and then this also, blue now is connected to with a cost of 81. Okay, so now pay close attention here, because this is when it's going to start getting kind of odd. So my red counter right before this iteration is now at index 0, 1, 2. I'm going to index 2 that. Index 2, which indicates this 3 right here, which is where the red counter currently is. It's on index 2 of the neighbors, or of the nodes that are in group 1. So my red counter here, my cost to get to, let me write this as an I. My cost to get to where I is going to be 4, which is what I currently is, minus my red counter at index 2, which is 3, which is 1 squared. So I'm going to have a 1 for that. Now this I is currently on the green group. If I were to look for, I erased my group table earlier, but if I know that, if I can look up that node 4 is in the green group, then that's group number 2. Group number 2 here, now I have a connection to red for a cost of 1, like that. Now, again, we want to advance now the red pointer because red is to the left of the red pointer's here, but I is to the right of it. So since red is to the left, red's allowed to advance. But when red counter goes to 3, that's going to indicate this 6 right here. That red counter is going to jump to here. My cost now to go from I to where the red counter currently is 4 to 6, which is 2 squared, which is 4. 4 is not smaller than 1, so that's not any better than it was. But I don't want to keep advancing this red pointer. My red counter is already to the right of I, which means now that I'm done, I'm going to take a step back to the previous one. We're going to drop the red counter back down to 2, so it goes back to node 3 to get ready for the next check. Let's see, that was a 6. We found the cost to connect from I to red. We're going to do the same thing for blue. I is currently at 4. The blue counter still is at 0, which is still node 12, which is still this right here, which is 8 squared, which is 64. So that's 64 there. 64 is now the cheapest way to connect from group 2 to the blue set, so to the blue set of nodes. So I've got that now, 1 and 64. Blue doesn't need to advance. The blue pointer doesn't need to advance, or it goes backwards. I is going to move forward. Now notice the red counter is still at 2. It's still indicating this 3 node here. So now once again, I check my cost from this node here, node 5 to red. It's going to be 2 squared, which is 4. And then I advance the red pointer because I might as well to there. I then check from 4 to 6, or from 5 to 6, since I is at 5. That's going to be a cost of 1. And then once again, the red pointer is going to take 1 step back. Red pointer is going to go back to 3 again. So it stepped forward to 6. It didn't want to keep going after that because there's no reason to move away from I. We repeat the process with blue. From 5 to 12 is, what is that, 7, 49. And then I advances to here. And it's pretty much going to proceed like that all the way through. Every single time you take a step forward, let's actually look at what the red pointer does here. So once again, then we check the cost from I, where it currently is, which is 6, to the thing indicated by the red counter, which is 3. That's going to be 6 minus 3, which is going to be 9. That's your cost so far. But then we can advance the red counter. Red counter will catch up to it, and this is how you're going to end up with the zeros. It will find every red node will be found to be a distance of 0. We advance the red counter now to 3. That indicates the 6 right here. Since I is 6 and this is 6, the difference of those is 6 minus 6, which is 0. That's how that 0 is going to end up here. And then again, since red counter is caught up with I, there's no reason to move it forward. If they're equal, there's also no reason to move it backward. Repeat the process with the 12. 12 and 6 is 36. And then I is going to advance to 7. And again, repeating the process, checking backward to the red counter, advancing the red counter. In this case, then they're equal. That'll come up with another 0. This is going to come up with 25. I is going to advance again. Now we're back to green again. Actually, this one should have been getting updated. That should be 25 now, 25. All right, back to green. Green now, I is equal to 8. Red counter is currently, actually it's going to be at 4 now. Red counter is at 4, which indicates the 7. Red counter is never going to move again. Because again, there's no reason for the red counter to move away from I, wherever I happens to be. So since red counter can't go forward because there's no more red nodes and also can't go backwards, the red counter is going to stay here, similar to how the blue counter has been staying there the whole entire time. And we'll get to blue in a minute. Blue is going to do the exact same thing. This was a green node. Okay. So we'll check from that green node back is going to be a cost of 1 to connect there. Always checking these. We already have a green connection for cost of 1. Then checking the connection to blue is going to be 12 to 8, which is 4 squared, which is 16. 16 is cheaper than 25, so actually now have a better connection to blue. I'm going to update that to 16. I advances. This is going to connect to the cost of 4. This is going to connect to the cost of 9. Red pointer can't advance. I is going to advance. These are all going to go by really quick because the red pointer can't move and neither can the green pointer, neither can the blue pointer, because the blue pointer can't move away and the red pointer can't move away. I is going to get here. Cost here is going to be 9. Cost here is going to be 4. Again, because that's, this is 9 because it's 10 minus 7 squared. This is 4 because it's 12 minus 10 squared. I advances again. Connection from here to red is going to be 16 now. Connection from here to blue is going to be a cost of 1. That's a new best cost here. I've been lazy about updating this, but this would have been updated to 9 and then 4 and then now 1 finally. 1. Also, these I haven't been updating group 3. Yellow is group 3. So this one here would have updated to 9 for the red on the first one. Then the 16 would have been ignored because it was higher. On the bottom, it would have been updated first to 4 from this one right here, and then updated to 1 for this one right here. Obviously your code's going to be consistent, even though I'm not being consistent. Yeah, it's going to update your distance to red and your distance to blue every time it does an update. This is going to become a 1. And then I is going to advance again. So now I is finally caught up with the blue pointer. And this is also, I want to make sure you see how this works, because this is going to work the same way with the red pointer. The rules are the same. I is here. The blue pointer is here. Cost from I to red is going to be 12 minus 7, which is, geez, what are we at? 1, 2, 3, 4, 5 nodes, 25. 25. I'm doing so much arithmetic, my brain is starting to shut down. All right, and then my cost to blue here. For my blue pointer, my blue counter was already on that node. I erased it on accident. My blue counter being at 0 right now, which indicates the node 12. My I being at 12 means my cost here is 0. So then my cost for group 4 to red is going to be 25 is better than infinity, and 0, obviously, because that's its own node. The I is going to advance. The blue counter for now is going to stay where it is. I is going to go to 13. That's now the yellow group again. It's group 3, just remember. Okay, cost to connect to red is going to be 36. Cost to connect to blue is going to be 13 minus 12 squared, which is 1. Now, for the first time, the blue counter is going to advance. Blue counter goes plus plus, which is going to make this a 1. That now is indicating the 15 node. Blue node advances to here. Cost from here to 15. 15 minus 13 squared is going to be 4, which is bigger than 1, so that's not any better. Move the blue pointer back, because again, it's ahead of I, so it's got to move back 1. Blue counter is going to go back to 0. Same exact thing that the red counter did, which means now once again we're indicating node 12. Then I can progress to the next node. I gets to here. Okay, cost for this one to connect to red is going to be 49. Cost for this one to connect to the blue pointer here, that's I of 14. Blue counter indicating node 0 is 12, which is going to be 2 squared, which is 4. So best thing we've seen so far. Blue counter goes up to 1, advances it to that 15 node again, which means the blue counter now is going to move to the last node here. 15 minus 14 is going to be 1. So that's now a new best cost of 1 for that node. Oops, this one is now going to be 1 with I here. I advances, I guess the blue node, sorry, the blue counter has to run back to 0 since it's ahead of I currently would roll back. Blue counter goes back to 0. This is now once we got node 12. Then I advances to I here. So then comparing to the blue node, that's going to be, or I guess comparing to the red node first, that's a cost of 64. Comparing to the blue node where the blue counter currently is, that's going to be 9. Blue counter can advance, and they're equal to each other. That's going to update to 0. which means that now, I guess that's still 0, and that's not going to change anything. And then that's going to be done. Okay, so now that we're done with that, we go through and look at all these pairs. 0 plus 81 is 81. 1 plus 1 is going to be 2. 9 plus 1 is going to be 10. 25 plus 0 is going to be 25. And out of all those numbers, 2 is the lowest number, which indicates group 2 is the best group to connect to. Group 2 was the green group. You can see those 2 nodes, if you remember all the way back to there, those green nodes. Group 2 consists of nodes 4, 5, 8, and 9. And we can go back and look. Our connection to red was right here. And our connection to blue. Where's my connection to blue? I got a 1 there. That might have been a 10 and I erased the 0 on accident, wasn't it? Yeah, no, that would have been a 9. Cheapest connection to blue. We'll go through and double check our work. I had a 64, a 49, a 6, and a 9. Yeah, that should have been a 9, not a 1, which actually means this is 10. 10 right there, 10, 25, and 81. So actually then that turns out that both the yellow and the green group had an equal connection, because my green could have connected to red with a distance of 1 and then to blue with a distance of 3, which would have been a total cost of 10. But yellow, as it turns out, also could have connected to red with a distance of 3 and then blue with a distance of 1, either here or wherever else, which still would have been a distance of 10. Okay, so it's a big algorithm and there's a lot to do. Just to kind of do a real quick recap, and then that'll be the end of the video. So looking at any of these groups, the first thing you want to do, put these into an adjacency list. Use your adjacency list, do a depth first search to figure out what group everything is in. Set up your iterator with a for loop to have I run from the first node to the last node. Set up a red counter for each member of each group. We want to have each group together with the nodes that are in the group, especially for groups 1 and group for the first and last group. We really only need it for the red and the blue group, but having it for each group doesn't hurt. So that way the red counter can iterate through those. We need to know what our best connection for red connection and our best blue connection is for each of those groups, groups 1, 2, 3, and 4, all of which are going to start at infinity. Infinity, 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 infinity. Let your eye run through all the nodes. Make sure you keep your red counter on either side of the eye at any time. Don't let it go past the eye. Make sure you keep your blue counter on either side of the eye at any time. So as your eye is advancing, your red counter is kind of orbiting around your eye. Your blue counters are kind of orbiting around your eye. Obviously, if your first blue node is way over here, then at first it's just not going to move around and it won't start orbiting around the eye until the eye gets over there. Run your eye through. Every time you do an update, make sure you're updating what the best connection is to that particular group that you've connected to. Once you get done, go through each of the groups and figure out which one has the smallest sum of your red connection plus your blue connection, which would indicate having the cheapest total cost of connecting to both red and blue. Good luck with it. I know it's a big one. I probably will do a coding walkthrough this at some point, or at least post the code that I have for this. And I will talk to you on the next one.